Hi everyone. Quick introduction from Fraunhofer IPA side. So I just joined, so I'm gonna moderate this meeting right now. Vishnu is the project manager for the ROS Industrial Consortium in Europe. And I wanted to talk about the upcoming events before starting the presentations. As you see on the screen, there will be a meetup in Stuttgart next month. Also, there will be a ROS Industrial Conference after the ROSCon in Odense. All information are on the website. We will be also present at the SPS fair in Nuremberg in November, so you can see us in the booth from Fraunhofer IPA. And we will organize in December a training, a ROS2 training. We will also give you more information per email or via the newsletter. And there will be a ROS tooling training also in January. Those are the next events. Also, as you know, you don't have access for the basic training from the construct for now, but this will be cleared in the next weeks. So just briefly on the conference in October, this was commonly organized by the DTA, Danish Technological Institute, and Fraunhofer IPA here. So for today, we will start with two presentations. The first one will be held by Mikel, Bueno, Viso, and Dr. Seemal Asif from IFRA Cranfield. Topic will be the sim-to-wheel robot control with Gazebo. And the second presentation will be from Manuel Muth and Dennis Stogel on the Modbus hardware interface. So I would say, Mikel and Seemal, the floor is yours.
Thank you very much, Yasmin, for giving us the platform and also inviting us for presentation as well. I'll just share my screen. So here we are. We will give the overview of different repositories that we have created. So at IFRA Cranfield, I'll just give you the overview of the IFRA Cranfield as we go along. But before we get into how we will take the whole presentation is, we'll give you the idea about what IFRA is as a group, what we are working, and give you some of the information about one of our projects on which we developed these repositories, which we will be talking today. And then Mikel will be taking you through the, going deep diving into the technical side of those repositories and what can be there. So now if we start with, let me just put it into the presenter mode, so it's much easier. So IFRA is basically it's part of Center of Robotics and Assembly Center at Cranfield University. We call them as a center. It's basically a department of robotics and assembly at Cranfield University. Cranfield University, just to give a bit of idea about the university itself, we are the only research-based university in UK, and we don't have any undergrads, so we only have the research students, PhD students, masters, postdocs, researchers, research fellows, and academics in the university itself. And we do have heavily collaboration with the industry itself. So Airbus, Rolls-Royce, a lot of European partners are basically, we are working on mostly on the research grants and research projects. So IFRA is basically, we launched that group 3 years ago. I launched it with Mikel, and now we have quite a lot of participants in this group, a lot of members. So we are working on the flexible manufacturing side of this, and also we also have the smart robotics as a part of it. We also have the human-robot collaboration, understanding of the trust and fatigue and those type of aspects as well. We are also trying to understand the human emotions. And apart from that, metrology is also becoming part of the group itself. So anything that is related to the flexible manufacturing, flexible assembly, and robotics is basically the part of it. It's not only the arm robots that you can see at the moment in the picture. We also have the drones and the mobile robots as well. So, and these are basically coming from the Center of Robotics and Assembly. So we are heavily resourced through the Center of Robotics and Assembly. What do we have here? This is our lab, and a bit of idea about our lab. So we have a couple of industrial robot arms. We also have now, and we also have the robot dogs, so like small to big scale. We also have mobile platforms, which you can see here, the MIR here with the UR16E on top. And we also have a couple of ABBs within our center as well. And apart from that, we have a quite huge lab with 3 set of Airbus A320 wings, which are part of our research. And that is the reason why a couple of our projects has gone beyond the level TRL 6-7, and one of them is currently at Airbus, so, which means we have passed their CISP and different tests in order to make sure we can transport it to the vicinity itself. We work on human-robot collaboration, and that's where the safety comes in. So we do take it seriously. We do have a lot of state-of-the-art metrological equipment as well, which we use basically for our research. And as I said earlier, we do have 3 full set of Airbus wings. 2 of them have flown. One of them has never flown. That's a China wing itself. So regarding the R3M project, I'm the investigator on the R3M project and also the technical lead on the project itself. We have 2 more universities involved on the project, Loughborough and the University of Sheffield, and also a Catapult Center, AMRC Sheffield. And I noticed they are also partner on the ROS Industrial as well. They are member of ROS Industrial as well. So we do, what we are trying to do is trying to make the system reconfigurable, manufacturing system reconfigurable, because hardware-wise, there is a lot of things that has been done in reconfigurability, but software-wise, there is really very limited that has been done in terms of, for example, if we are running a system, a cell in the factory floor line, and we try to change the cell from pick and place to a cutting cell to a welding cell, then there will be a lot of software-wise, you need to change quite a lot of things. So what we can do to make sure that we can make the programmer life easier and also easy to maintain systems as well. So I just give the holistic picture. It's a very an example coming from kitting to welding, but what really we can do in order to make sure if we change any end effector onto the robot, industrial robot, or anything within the cell itself, we are changing the positioning. Can we do something to make sure that it is reconfigurable? And that's where we are using ROS2. So we initially started with ROS, and then ROS2 was there. So my idea was to make sure, because ROS has some shortcomings, and I was going through the path in which I was uncovering them. And we were quite interested in the industrial aspect, real-time aspect, and how ROS2 has basically overcome those things. So we decided to basically go through with the whole project by using ROS2, and our architecture, which you can see here, is quite reconfigurable in order to, it can be deployed on services. So it's basically service-oriented architecture. So we have service-based architecture accessible through different platforms, and also having the database management system allowing us to make sure we can deal with different repositories, deal with the data management, and also can basically digitalize the system with ease as well. And we have the resource management system. We have the scheduler in order to make sure that we can schedule the jobs, can run multiple cells at the same time. We are going through at the moment through that phase as well. And we can basically attach with multiple, we can apply this technology on various hardware. And one of the things that you have seen is through our public repositories. So we have currently 15 plus repositories on our IFRA Cranfield, and 7 of them are at the moment publicly available, which we think are really helpful for the community. So I now give handle to Mikel to
Perfect.
talk more technically into it.
Cool. Yeah, thank you, Seemal. So as Seemal has mentioned, this R3M project pushed us to develop a software that was able to realize that reconfigurability. We do have the hardware, the reconfigurable hardware available, but we had to develop a software which was able to realize those changes in the manufacturing process and obviously realize those through that reconfigurable hardware. And at the beginning of the project, we realized that ROS2 had that potential, but there was a huge lack of documentation and huge lack of availability of different packages that we could use in order to execute and simulate and control the robots in a standard way. So at the beginning, and as a first step of this process, this project, we decided to develop some packages that could, first of all, simulate the robots in Gazebo. And when I say the robot, I say any robot manipulator, any robot arm that can be controlled through ROS2 and move it. So at the beginning, we decided that we had to develop some standard packages that could execute those simulations in the real cell. And obviously, starting from those simulations, then be able to understand and to control and operate those robots in the real cell. So we ended up with some standard packages that if the information and specifications of the robot were provided on a standard and a specific way, those simulations and that operation of the robot could be operated and could be realized exactly in the same way with our packages. And those packages obviously are the packages that are available in our repositories that I will explain and I will introduce after. So in the end, we ended up having robot simulation ROS2 packages that were simulating the robot in Gazebo. This follows more or less the standard procedure that we could see with previous ROS1 packages in the internet, obviously in GitHub and within the ROS Industrial Consortium, of course. So we do have 3 packages: robot simulation package that obviously simulate and do have the information in Gazebo, move it packages, and the robot bring up packages. And after developing this as the second step, and considering that we already had that ROS2 based control and simulation of the robots, we realized that it was a lack of let's say control and operation modes of the robot, because nowadays if you do have a teachbent and you can control and generate and operate those robots using different sequences, executing different programs very easily with different types of movements, and that wasn't available and intuitively, it couldn't be used intuitively we couldn't find out within ROS2 documentation. So what we did, taking advantage obviously of different ROS2 communication methods, which are the topics, services, and actions, we encapsulated what we thought were useful move-it functions in order to operate the robot in different ways. We encapsulated those functions and those classes into different ROS2 actions and ROS2 topics in order to be able to operate the robot intuitively using ROS2 and using Python. So at the beginning, you can see that we encapsulated a ROS2 topic called ROPOS that can be easily accessed in order to obviously access the end effector pose of the robot during execution. And next to the ROS2 actions graph, you can see the move and move ROS2 action service. Thanks to those actions, what we did is we encapsulated different robot motion types into these 2 actions. Move action means that we can move the robot with different action movement types. Move J in order to move it with joint positions. Move L to move it on Cartesian paths, to move it linearly. Move R to move the robot, but only an independent joint. And move rot to move the robot according to some inputs, which are the rotations, Euler angle rotations. And then apart from that, we do have the rob move, which directly moves the robot to a specific end effector pose. And this movement, this ROS2 action server is especially useful combined with the rob pose topic, because if you know the exact pose of the end effector, thanks to that ROS2 topic, you can then accommodate that and play with that in order to define the next end effector pose. And thanks to this, what we could develop is different Python classes in order and different Python functions that enable the user to control the robot very easily and very intuitively using a Python script rather than having to play with the MoveIt's API or different ROS2 actions or the ROS2 controllers directly. What we did was combine MoveIt's API and MoveIt ROS2 actions, ROS2 topics with Python by developing those Python clients in order to control the robot more intuitively. And you will see, Seemal, if you go into the next slide, please, that we could develop sequences, programs very easily, very intuitively that allow the user to execute different applications easily using ROS2 and using, obviously, MoveIt. And what you can see in the video is an ABBI 120, sorry, in both simulation and the real cell using the exact same program executing this cube pick and place task. The program is exactly the same. The only difference that you can see is a small delay because closing and opening the gripper in Gazebo adds a little bit of delay. But apart from that, the program is exactly the same. So thanks to this implementation, we can operate the robot exactly in the same way in simulation first. And then after that is verified on simulation, we can deploy it and the behavior is exactly the same in the real cell, because obviously MoveIt is the entity controlling the robot. MoveIt is the entity controlling the program. So the behavior is exactly the same. And another feature, another functionality of our system is that obviously if your robot can be controlled through ROS2, if your robot can be controlled using MoveIt, it can be controlled through our Python clients, through our Python functions and classes. So this allows us to control different robots. And this is a UR3 robot, which is in the lab as well, in both simulation, Gazebo simulation, and the real cell, being controlled exactly in the same way as the ABBI 120 was controlled in the previous slide. So this feature or this Python-based control enables us to do that hardware abstraction, and we get a system which is completely robot agnostic. We don't care about the robot. We can execute these programs, these sequences exactly in the same way in both simulation and the real cell, obviously. So yeah, and in the end, we end up with this architecture, with this ROS2-based software architecture, which is made by, on top, the robot bring up ROS2 package with a specific ROS2 driver, obviously, that enables that interconnection and that ROS2-based control of the real robot, and the Gazebo simulation ROS2 package, which contains the specifications and the URDF of the robot, the MoveIt ROS2 package, which obviously contains the parameters that enable that MoveIt-based control of the robot. And in gray, at the bottom of the slide, you can see that robot abstraction that we get thanks to the encapsulation of the robot movements and monitoring that I have explained before. We do have the move and ROS2 actions that control the robot, and the raw pose and object pose, which I will explain later, ROS2 topics that allow us to monitor the end effector pose and the state of the robot during execution. And why is this particularly useful? Because obviously we can get a standard ROS2 system that enables this control and simulation of the robot, no matter which robot, end effector type, or even application we've got. And I say application because since our system and the robots can be controlled through Python, any external component, any external software or hardware that could be controlled through Python can be seamlessly integrated within our system. And that allows us to combine our robot control and robot monitoring with any external application that could be designed in Python. For example, any YOLO-based object detection, any OpenCV-based image processing task, or any AI application that can be designed and operated in Python. And that is extremely useful because it allows you to combine robotics and any other research in software. So if you go to the next slide, yeah, this is our main repository, which is available publicly in GitHub, where we basically have a huge database of different robots. The robots that we have publicly released are because obviously have been pushed because of our project. Those are essentially the robots that we do have in the lab, and that's why we have released the packages. But we obviously, in the future, we would be more than happy to collaborate and to upload much more robots, and you have a huge database of different robots that work using our system. We do have different end effectors as well. And apart from that, another obviously, and that's what Seemal is pointing now, another cool feature is that we do have a unified launch platform as well. Rather than having independent launch files or independent ROS2 packages, what we do have is we do have the ROS2 database and the ROS2 package with robots and end effectors, and with a single launch platform, with a single launch file, we can launch the different simulations and robot bring up nodes in order to control the robots. And this is because, as I mentioned before, we do have a standard way of executing these environments, and the robots are, no matter the manufacturer, the model, the brand, are controlled exactly in the same way. And yeah, in a nutshell, we do have Python classes for the execution of robot movements and effector movements, sequence execution, robot state monitoring, as I mentioned before, for the robot state topic, and we have different features as well. And one of them is that we can spawn different objects into Gazebo, because in our project, we do have one of our partners working for object recognition and object detection and 6-degree of freedom pose estimation. And one of our the features that we needed in order to test that was that we needed to spawn objects randomly into Gazebo in order to test those nodes. So that, as an example. And our future plan for the repository is to obviously increase the database with different robots and effectors, and why not different features, different robot movements, why not different ways of monitoring the robot, the end effector state, anything. Create proper documentation and instructions to use it, because now if you access the repository, you will see that we've just made a huge update, and I still need to update the documentation and instructions to execute those new features. We do have an HMI to operate the robot, a PyQt5 based HMI that enable us to execute different programs and movements more intuitively, rather than having to define, for example, or having to execute ROS2 actions in the terminal. We do have an HMI that execute those ROS2 actions using more intuitive buttons and displays. And another cool feature that we're planning to introduce in the future, considering that our ROS2 packages are completely standard and are exactly identical for all the robots, we are planning to generate and create an automatic generation of ROS2 packages feature. So we can, based on some inputs, which could be URDF specifications. When I say specifications, change velocities, accelerations, maximum, minimum angles. All those specifications could be straightforward turned into a ROS2 package that follow our standards for our execution of the robot simulation and control. And as a last slide, we do have additional ROS2 packages and plugins that obviously have been developed, because in order to fulfill the different necessities that we had in the project. For example, one of the main disadvantages I've noticed using Gazebo and ROS2 was that the object grasping plugin wasn't fully developed or wasn't fully available for us to use properly. That's why I developed a link attacher plugin that basically does is it attaches objects to the robot's end effector in order to simulate that object pick and place in Gazebo more intuitively. It does not simulate grasping effectively, because you are somehow tricking Gazebo, you are somehow attaching the object directly to the end effector, but it does the job. And since we needed to simulate and verify different applications using Gazebo simulation before actually deploying them into the real cell in our lab, this was especially useful because it allows us to for example, simulate different kitting applications in Gazebo. We developed a conveyor belt plugin. We didn't develop. I basically took what is developed in ROS1 and I basically migrated it into ROS2, and it is available in our IFRA GitHub package as well. And apart from that, I developed couple of plugins that enable us to fully monitor everything that's happening in Gazebo. I developed a plugin that allows the user to access the exact 6 degrees of freedom pose of any object and any robot link using different ROS2 topics. So if you add a little line with the plugin to the objects or robots URDF file, and then you spawn that object or robot into a Gazebo simulation, this plugin is activated automatically and it publishes the pose of that specific entity as a 6 degree of freedom ROS2 topic into the ROS2 environment. And it's especially useful because for us, that we evaluate and test different object detection and 6 degree of freedom pose estimation modules that we develop using YOLO or using OpenCV, we can compare the results that we get with the exact truth, the ground truth, which is the values that Gazebo are giving us from this plugin. And apart from that, yeah, we do have a UR3 robot with a robotic Taiki gripper, and what I did is I encapsulated the TCP IP based connectivity of that and control of that robotic gripper into a ROS2 service, and thanks to that we can control any robotic gripper which is connected to a UR robot as well. So small developments that we are doing, and that obviously we are making available in GitHub, and we wanted to share within this ROS industrial meeting. And yeah, that's it. A small slide with our different social media channels. We do have a YouTube channel within IFRA as well, where we share different videos of different executions, and especially that GitHub page where you can find all this information and all the source code for all our packages, all the robot simulation and control packages. Thank you very much.
Yeah, one last thing that I want to reinforce is that our 2 more repositories will be coming up towards the end of this month. So our paper has been accepted for IEEE case. Once the paper is published, we are publishing the repository with it, and also with IEEE Indian as well. So Mikel is basically doing around the Europe this month to present our papers, and also we will be publishing 2 more repositories, and 1 more repository will be coming up. So one of our other paper has been accepted as well for our SIM journal, so elsewhere journal. So we'll be publishing it as soon as the minor corrections that we have done went through as well. So 3 more repositories to look for.
Yep. Yeah, we're publishing papers, and ROS2 is present in all those papers, which is very good news. And we are obviously mentioning and explaining all the technical details of this architecture and developments in those papers.
Yeah.
Yep.
So any questions for us?
Yeah, thank you very much, Seemal. Thank you, Mikel, for the big overview of your lab and of your activities, and on the repository also. I think it will contribute a lot for us, at least at Fraunhofer, and of course for the consortium also. Let's see if there are some questions. Feel free to ask.
Hi, this is Gijs from TU Delft. I was wondering whether your motion API was based on any existing standard, like PLC Open or OpenCUA, or maybe even the SRCI, or did you design something completely custom?
No, we didn't follow any of those. What we basically did is we used the standard ROS2 drivers of Universal Robots and ABB, and using those and the standard motion planning that MoveIt is providing. Obviously, we are using PIL's motion planner. So we encapsulated what we've done is we've encapsulated those motions into the different movement types. But what we are doing is we're connecting to the real robots. It's straightforward through TCP/IP connectivity using the standard ROS2 drivers we've tested it into using Universal Robots and ABB at the moment.
Yeah, just to add to that question, we already have expertise in working in OpenCUA on different various other projects, specifically with the industry, where they do not want to see the ROS. Basically, so we have done a lot of work on the OpenCUA integrating the robotic system cell as well as the peripherals, including different perceptions and metrology by using the OPC UA standard as well. So we do have a lot of work in there, but of course, though that is not publicly available. But our next venture would be include a couple of more robots, which we do have in our lab. For example, Stably. We do have variation of Stably as well in the lab, as well as we have huge conveyor belt with its own controls. We want to include that, and also a lot of more toys are coming in the lab, which we will be including, but also we will be making sure, because one of the essence of the project was to make sure that we can integrate with the legacy systems. So that will be one of our venture or backdoor to in order to make sure that we can integrate with the legacy systems as well.
So apologies for not being clear. What I meant was you added a layer on top of the different robot drivers that lets you sort of abstract away the different interfaces that they have. And you created a ROS API for that. So you had some custom action servers and some topics, I understood. But I was just curious whether you modeled any of that on an existing sort of industry standard for these kind of interfaces. I mean, PLC Open has a bunch of standardized messaging interfaces.
Yes.
OPCUA as an information model for
Yes.
robotics specifically. So I'm just curious whether you modeled it on any of that or whether it's just a custom
No.
interface, which is not bad, but it's just a different approach, right?
Yeah, it's a different approach, but we do model. So when I begin with the information about the project itself, our system is basically based on the web services type architecture. So we are making sure that our system is available on the web services, but we do have that I'm illustrated earlier as well. We have planned to utilize the OPC UA, but we haven't modeled the whole system based on those standards.
Right. Okay. Thanks. If no one else has a question, maybe another one then. Why did you decide to go for a mono-repo approach instead of making separate repositories for the different robot types and services that you support?
Shall I answer to that one, Seemal?
Yeah, go ahead.
Yeah, so what we basically wanted is to obtain a standard architecture that would, for example, and that's one of our cases, what happens if within a manufacturing process you have to change the robot and you don't have an ABB available and you have to put obviously it's a silly question, but because you're not going to put a UR3 word where you had a IAB 120, but we needed to add that reconfiguration case where you change the robot. And what we basically wanted to get as a final product, as a final software middleware, is a standard system that would allow the management and the control of any robot, no matter the type and the model. That's why we basically I wanted to let's say reflect that on the ROS2 package as well, and standardize it as much as possible in order to as well simplify the operation. Why not? Now, rather than having different launch files, different packages, I do have a standard launch package that enables me to launch to use only one file with different input parameters and launch the robots and launch the simulations exactly in the same way, no matter the robot and then the vector type. That was the reason.
But for that to work, it doesn't all have to sort of live in the same repository, right? You could still have separate repositories, separate.
Yeah, you're right. And obviously for the different applications and different environments, I'll give you an example. We do have a cell at Cranfield that does have an enclosure where the ABB IAB 120 goes. For the different applications, yes, we do have different packages. But for the standard, let's say, raw packages where we do have the information of the robot only and the vectors only, no environmental or CAD information of the cell or any robot workspace. For those standard packages, we do have only one repository where we are saving and we are storing the information of the different robots and then the vectors. But then for different applications, different specific or custom packages, yes, we do have different repositories. And for example, those two that Seemal was mentioning before were two repositories where we are doing automated kitting in two different scenarios. For those, yes, we do have two different packages, two different repositories that we're gonna release publicly in GitHub soon.
So the idea was why we released those robots and why we released the sim to real robot is because we have gone through that problem. We have gone through that issue that we were not able to find anything standard in those. And specifically when we went into the motion planning sequence, there were issues in the motion planners. So we thought it would be useful for people if we release them. And of course, the project is on EPSRC, so we want to collaborate back into the community itself. And that was the whole notion. So we were like, if we release them, it will be useful for the researchers out there so they can start where we are stopping.
Okay, thank you for the questions and answers. And I think we will need to switch to the next topic. Thank you very much. And